So here are some other considerations. So in reality, it is difficult for rainfall to occur with uniform intensity and long duration. Yes, so when selecting a storm event for unihydrograph analysis, a rainfall event with a relatively short duration must be chosen. So you have to choose a rainfall event with short duration because in real life it's hard to get a uniform intensity and long duration. So short duration storm events are more likely to have relatively uniform intensity and produce a direct runoff hydrograph corresponding to a unit depth of effective rainfall. So since it is practically difficult for rainfall to be evenly distributed, this is also true, over an entire watershed, the unihydrograph method is more suitable for relatively small watersheds. Therefore, if the watershed area is too large, it should be divided into sub-basins for separate analysis. The recommended watershed area for applying the unihydrograph method is generally between 2 km square and 5,000 km square, but this may vary depending on the watershed characteristics and data reliability. So when we're doing this in real life situation, we're gonna have to divide the basin or the entire watershed by into different sub basins, and this is what we do when we do research as well. So although the principle of equal base time, principle of proportionality, and the principle of superposition may differ from actual hydrologic conditions and thus may cause some degree of error, these assumptions are considered very useful when applying the unihydrograph method in practice. Moreover, errors associated with these assumptions are generally much smaller than those due to measurement errors, such as infiltration or evaporation. So overall, the method of unihydrograph is very useful, although it does have some errors. So next we have the derivation of the unihydrograph. Okay, so unihydrograph from a single storm event. The procedure for deriving a unihydrograph using a single storm event and its corresponding direct runoff hydrograph can be summarized as follows. Number 1, from rainfall records, select a storm event with a suitable duration, uniformly distributed rainfall over the watershed, and significantly contributing to direct runoff. Prepare a hydrograph, so that's graph with the bars, okay, with uniform time intervals. So these time intervals should be uniform. And construct a rainfall intensity chart using the rainfall runoff data throughout the direct runoff hydrograph, by separating base flow from total stream flow. So this is total stream flow, and then base flow will be a flow that we separate by normally you just try to find a value that continues throughout, and try to find a value that where you can separate like this, and then between base flow and then the direct runoff. And finding this value is, well, it's kind of up to you. You have to see the data, and then you have to find a point where you can separate the rising limb part from where it starts to build up to this curved area. I mean, this method is quite intuitional. You have to do it yourself and try to find the right approximate place to make this separation between base flow from total stream flow. Okay, so to determine the area under the direct runoff hydrograph, which gives the volume of direct runoff, divide this volume by the watershed area to convert it into a depth of direct runoff. This value can be obtained using equation 10.1 below. So you're dividing the volume of this dr by the watershed area to convert it into depth of direct runoff to get a centimeters, millimeters, or inch value. Okay, so this is the equation to get the depth of direct runoff. Okay, so RD. Okay, so delta T is again time interval of the direct runoff hydrograph in hours. Q sub I is discharge at each time interval of the direct runoff hydrograph. So that's the value you get when you draw a hydrograph, so value here, value here, value here, value here, value here. Okay, N equals number of time intervals, A equals discharge drainage area of the watershed. So So step number 5, divide each ordinate of the direct one-off hydrograph by the value of R sub d to obtain a dimensionless union hydrograph. So this happens after you get R sub d, okay? So divide each ordinate of the direct one-off hydrograph by the value of R sub d to obtain a dimensionless union hydrograph. So an ordinate is like a block of time interval. So like like a time interval from here to here and from here to here. So each interval that's happening like this is called ordinate. Okay, that's the term, ordinate. So you have to divide each ordinate of the direct one-off hydrograph by the value of R sub d to obtain a dimensionless union hydrograph. The effective rainfall hydrograph for this storm is assumed to be uniform in intensity over its duration. Therefore, the duration of the union hydrograph is determined to be equal to the duration of the effective rainfall. Okay, so the duration of union hydrograph is equal to the duration of the effective rainfall, because we assume that the rainfall intensity is happening equally, uniformly, the same throughout the entire area. Okay. So we next have the representative union hydrograph. So even if storm events have the same duration and total rainfall depth, each effective rainfall event may produce different union hydrographs due to variations in storm direction, rainfall distribution, and watershed characteristics. Therefore, it is common to derive several union hydrographs from multiple storm events and then combine them to obtain a single representative union hydrograph. Okay, so a representative union hydrograph is obtained by averaging several individual union hydrographs. So we're basically making multiple of these and then combine them together. So as shown in figure 10.4, the average of the times to peak and the average of peak discharges are calculated. So we calculate the average of times to peak and the average of the peak discharges like this. And then use as reference points for developing the representative union hydrograph. For example, if there are 3 union hydrographs with times to peak and peak discharges, the average values can be found using these equations. So we're getting like the average T sub P, average Q sub P. And then the representative shape of the union hydrograph is determined by considering the shapes of the individual union hydrographs. When plotting the representative union hydrograph, the total discharge should correspond to 1 centimeter of effective rainfall. So this is easy to understand if you look at a figure. So here, so we have drawn 3 unit hydrographs. Okay, so we have T P sub 1, Q P sub 1, and then we have the second one and the third one, and then so T sub P is time. This is T sub P. Okay, so time to peak, and Q sub P is the actual peak discharge. So to draw a representative union hydrograph that can show so even if storm events, so in the case of storm events, because the storm is moving, we might need to have combine 3 different union hydrographs to make a 1 representative union hydrograph. Okay, so we do this by, like what I just explained, by taking the average of these values. So average of 1, 2, 3 to get this final value that helps us make this union hydrograph, because we know where the time of peak is and we know where the actual peak discharge occurs. So it should be like right here, and we can construct a union hydrograph that represents this storm event. And then next we have example 10.1. The average rainfall over a watershed and the observed stream flow are given in 10.1 below. Base flow is separated using the straight line method. So this is the method I kind of showed where you have runoff hydrograph and then you use like a straight line to separate between base flow and direct runoff. And the watershed area is 5,870 kilometers square. Determine A, the unit hydrograph, and B, the duration of the unit hydrograph. So table 10.1, average rainfall over the watershed and observed stream flow. So we have time and we have rainfall in millimeters, and then we have time again in hours, but this is time for the discharge. So we have discharge, cubic meters per second. Okay, so we basically have the rainfall, the average rainfall, right, and the observed stream flow. Okay, so we have the hydrograph and we have discharge hydrograph. Okay, and since the base flow is already separated, this is direct runoff hydrograph. Okay, so the time interval of direct runoff hydrograph delta t equals 6 hours. Let's see and check. So time interval between 9 is 6, 9 to 15 is 6, right? So it's 6 hours intervals. Time interval and duration of rainfall hydrograph is delta t 3 hours, t equals 12 hours. So, it's total of 12 hours. So that's correct. And delta t from 3 to 6 is 3, right? Then we have delta t equals 6 here. Sum of direct runoff hydrograph ordinates is 20,060 cubic meters per second. Base flow separated by the straight line method is 113 cubic meters per second. So what it's saying is this value down here that's been subtracted. And then the sum of direct runoff hydrograph ordinates, so it's basically summation of all this. Okay, you see this total? It says total down here. So it's the total of the direct, so it's the total of the direct runoff. So we had, so this is the original discharge, and then we basically subtracted 113 from everywhere, and we use 113 as base flow. Okay, because 113 is like the lowest value, and when you subtract it from the beginning to the end, you will get like 0 values here. So instead of having hydrograph that look like this, we subtract this area, so it becomes like this. So that's direct runoff hydrograph, and this is just normal discharge hydrograph. Okay, but because we subtracted 113 like all throughout, it becomes direct runoff hydrograph like this. Okay, so we're subtracting 113 from all of this. Okay,